vector quantity. And a scalar and a vector quantity are specific terms. Scalar applies to a term, a quantity that has only a magnitude. Examples of a scalar quantity might be like temperature. It's just 32 degrees Celsius in this class. That's all it is. It doesn't have a direction. It's not like up and to the right 32 degrees Celsius. It doesn't work that way. So it has only a magnitude. Example in this case, temperature is going to be 32 degrees Celsius. There's no direction associated with that. However, the vector, and I hope that you guys have all seen the movie, yes, Despicable Me, where of course the, go ahead, the main villain name is Vector, and there's a very famous scene where he's like, a vector has both magnitude and direction. I don't know if I got the voice right there, but the idea is that he kind of reveals that. And so vector quantities, for example, like velocity, which I will abbreviate with a V that has a vector hat on the top of it. That little arrow that's bisected across the long axis denotes that this particular quantity of velocity is a vector. So you'll notice that little hat doesn't show up on the T because temperature is not a vector. Velocity is a vector, so it's going to have a magnitude, let's say 12 meters per second, and then comma, it's going to have a direction. And the direction could be a lot of things. It could be an angular direction on a coordinate axis system, so it could be 172 degrees, or I could be using radian measure. It could be, 3.14 or pi radians. Or if I'm dealing with vectors that are only in one dimension, meaning only left or right, let's say along an x-axis on a traditional coordinate axis system, I could call everything to the right positive and everything to the left negative. And in fact, that's what we're going to do. There's actually a convention for vector direction when you're dealing with vectors on a coordinate axis. If it's a horizontal vector, to the right is positive. Just think of your coordinate axis here. This is the positive x-axis, and over there is the negative x-axis. So that would mean that up is positive and down is negative. So if its motion is only going up and down, we're dealing with, let's say, vector velocity on an elevator. And so we could say that the velocity of the elevator is 5 meters per second. In the downward direction, it would be negative 5 meters per second. You would use the negative sign to denote downward in the y plane. Okay, so vectors have hats. Other examples of vectors are force and acceleration. We'll be learning those things later. Of course, F would be the abbreviation for force. A would be for acceleration, and they all have the vector hat on it to denote, dude, you gotta have a direction associated with this number. Okay, so all that we're going to learn today is based on one concept, and that concept is quite simply the concept of an object's position. And position, in its most basic sense, is simply an object's location along a number line. An object's location along a number line. Now, technically, position is also a vector. Position is a vector because it could be positive or negative. So position is typically measured in SI units of meters. Meters abbreviated, of course, with a lowercase m. Meters are the SI units of position. And if this were a number line and I had some origin 0, I could have positions of -1, -2, and +1, +2, etc. Of course, that continues to infinity. So position is simply an object's location along a number line, and all of the meat from today's class is based on that alone. Sounds so simple. Object's position, I get it, where it is in space. So the very first kind of derivative, if you will, or the very first kind of subset of position or related to position is the concept of velocity. Velocity is simply the rate of change of position with respect to time. It's how fast your position is changing. So I could write that rate of change of position with respect to time. And the reason that I write it that way is because of those of you with some experience in the language of calculus are aware of what a derivative is. A derivative is a rate. And if you're not in calc and you have never heard of that word before, don't worry about it. I'm just making I'm basically making connections to to mathematical concepts that you'll be learning very shortly. The derivative is one of the very first things. Who's enrolled in calc right now? Who's already taken calc? Okay, so you guys know exactly what I'm talking about. For those of you who are taking calc this year, have you guys used the word derivative yet? Not yet. You will soon. You're probably doing limits right now, I assume. Yeah, okay. So the derivative is going to come shortly. And if you do it now, as soon as you start looking at the relationships between first and second derivatives in physics, you'll see it in calculus and you'll be like, oh yeah, I got this. And for those of you who have taken it already in calculus, you're going to be like, I already know what we're talking about here. Okay. So, and by the way, if you've never heard of a derivative and you're not enrolled in calculus, don't freak out. It's okay. It's not required to like be successful in the class, but since such a large fraction of our students have taken that level of mathematics, it's important to make those connections when appropriate. But it certainly won't sink the boat, so to speak. So it's the rate of change of position with respect to time. So the kind of the formal definition of velocity could be written that way, but I could also write it mathematically as delta v, the velocity is the change in position. Delta x with respect to time over delta t. The change in position over how long it took to do it. And for our math nerds, I'll write this in a different color. We could also say that velocity is simply dx dt, the derivative of the position function with respect to time. It's just kind of one way. Another way of looking at it, again, asterisk, only if this kind of stuff is starting to make sense to you. And it will, for those of you who are concurrently enrolled in calculus, you'll start to see that kind of notation very soon. It's simply how fast your position is changing. Speed, on the other hand, is simply the scalar form of velocity. You could very easily kind of articulate a correct definition of speed by simply saying it's velocity with absolute value bars around it. We don't care what direction it's going. So if it's an elevator and it's going up and down and you were worried about plus or minus 3 meters per second up or negative 3 meters per second down, if we specifically ask for the speed of the elevator, it doesn't matter, it's just the number, the magnitude only. So you would simply say 3 meters per second would be the speed in that case. So in this case, it's just a slight variant. Velocity is a vector. I'm going to put that in parentheses. Don't forget that velocity is a vector, and speed is a scalar quantity that has no direction associated with it. They're almost interchangeable with the exception that speed is a scalar and direction doesn't matter. If I take one more step, I'm going to introduce our last term for the day. Well, almost. We've got 2 more after this, but this is the heavy one. I'm going to put an asterisk next to this. This is my 11th year teaching physics. This is the idea that is always the most difficult for first year physics students. This does a lot of butt kicking in the first 2 weeks of your first physics class. And it's going to sound okay, but there's a lot of layers of complexity to it. So don't underestimate the complexity of acceleration. Acceleration, by definition, is the rate of change of velocity with respect to time. It's how fast, how quickly your velocity is changing. And velocity is already a rate. It's already the rate of change of position. So acceleration is like a double rate. It's the rate of a rate. How many people have heard the units of acceleration before in another class? What are the units of acceleration? Meters per second squared. How many people have seen meters per second squared before? How many of you have quietly asked yourself, but maybe never asked, what the hell is a square unit of time? What's a square second? Like, I know what a square meter is. It's surface area. What's a square second? Has anybody ever asked that to themselves before, but just kind of brushed it off and was like, all right, it is what it is? Square second is a just mathematical grouping of terms. It's nothing fancy. Because by definition, if the units of velocity are meters over seconds, right? It's your change in position with respect to time. This would be in meters, and the units here of time would be in seconds. So the SI units of velocity are meters per second. Makes sense, meters over seconds. But acceleration, by definition, is the rate of change of velocity. So I can write a definition for acceleration in this way. Acceleration is equal to my change in velocity with respect to time. My change in velocity with respect to time. And again, for the math nerds out there, we can see that acceleration is just the first derivative of the velocity function, or another way of describing that is that it's the second derivative of the position function would be another way of describing that. Or yes. Okay, so let's go ahead and add some units in here. In our numerator, we have meters per second is our units for velocity, and time is just seconds. So I have meters per second. It's the rate of a rate. And the last time I remember doing this in like grammar school when you're dealing with complex fractions is you just multiply by the reciprocal, right? So I'm going to take meters per second when I'm dividing it by seconds over 1. So I'm now going to multiply it by 1 over seconds, and that gives me meters over seconds times seconds, or meters per second squared. That's where the funky unit comes from. It's just another way, perhaps more conveniently, to write meters per second over seconds. I'm going to, at least for the first 2 weeks of class, I'm going to always write the units of acceleration this way, meters per second, because I don't want you to get confused with a square second, and I want you to develop some intuition with what acceleration is. It's how fast your velocity is changing. How fast your velocity is changing. I'm going to write just a couple more quick definitions up on the board, and then we're going to play with this with some graphs showing relationships between all of them. The last definitions I want to throw up here are displacement. Displacement is a vector quantity. I should have probably done this earlier. Displacement technically would be abbreviated with delta x, and it's simply your change in position. And it's a vector. Change in position. Notice that I use that notation over here, delta x. So technically, velocity is just your displacement over the time interval. And underneath that, I'm going to write one last definition for today. That's going to be the definition for distance, which is abbreviated with a d, and it is simply the absolute value of displacement. Oops. So it's basically, well, I'm going to simplify it for now and just say it's basically how far you went, but we don't care what direction it's in. It's a scalar quantity. Displacement is a vector. Distance is a scalar. Okay. This is one of those instances where the only way to